This meeting is being recorded.
I guess. All right, so the stimulus for the body temperature, I don't care which one you use, but I want you to know both, okay? So we'll do an increase in body temperature for this one, and then we'll go back and do a decrease in body temperature on the side, okay? So for the sensor, and we went through this in lecture, but for the sensor, what you're going for is you're trying to find a receptor in a location. So don't just give me thermosensors, it would be thermoreceptors.
So we still put skin, right? You want location, the location and.
Yeah. Okay, and that's going to be true for each of these, right? Thermoreceptors and skin. You can put in the hypothalamus too if you want to. You can give me one or the other one, or you can give me both if you want to.
So the integrator isn't hypothalamus?
It is. Yep, it is. You have sensors externally in the skin, and you have sensors internally in the hypothalamus. Mm-hmm. And so these are going to measure, they're going to measure the body temperature, and they're going to send signals to the integrator. And then Rena, what would be the integrator?
I have hypothalamus.
Perfect. The hypothalamus is an integrator, and that's not going to change. That's the same, right? Because the pathway is usually the same. There might be a little bit of a difference, but not with much of it, right? Okay, so the hypothalamus is then going to get the information from those receptors and measure it against a set point. And the hypothalamus says, hey, body temperature is too high, we need to bring it back down. It doesn't technically say that, but, and so the hypothalamus is going to send a signal to the effectors to get body temperature to go back down. So what would be the effector in this situation?
Sweat gland and blood vessels throughout the body.
Good. So sweat glands, so we can say skin, right?
Mm-hmm.
Sweat glands. And
Blood vessels?
thank you, blood vessels. Okay. Yeah. You're just naming the effectors. You're just naming the effectors. You're not telling what they're doing at that point. You're just naming them. Okay. And so what are these effectors going to do then? Brenda?
They're going to increase sweat in the skin.
Perfect. So they're going to increase sweat, and the blood vessels are going to vasodilate, right? To release heat. And you know that when you get really hot, you get flushed, your cheeks get pink, right? Okay, and the result should be then a drop in temperature. Okay.
I have a question.
Go ahead, John.
So for the increased sweat, I mean, I know our body releases sweat to release heat as well as the blood vessel dilation. But is there also, I mean, you can consider the sweat and the wind chill factor as a cooling element too, or no? Or is it more just the body's function of releasing sweat as?
You can think of it that way too, but there's a lot of things into play, right? Okay. So you can think of wind chill, you can think of wind, right? When we have the Santa Ana winds, we obviously lose heat faster. You can think of that. I just don't want you to include it in this because it gets really messy, right?
Right. Okay.
You can include behavioral responses like taking off clothes, putting on clothes if you're cold, but just make it as simple as you can when you're first learning this stuff.
Like pertaining to the body. Okay.
Yeah. Okay, and then if we have a drop in temperature, the thermoreceptors in the skin and hypothalamus are going to be the sensor. The hypothalamus is going to be the integrator. The effector could be the same or it could be different, right? It could be, let's say, skeletal muscle. Right? It could be skeletal muscle, and the skeletal muscles could shake, right? Or shiver. And that could increase body temperature, right? There's a lot of different ones you could have for this. You could have erector pili muscles in the skin, and you could have them contract and form goosebumps and trap heat to increase temperature. You know, behavioral modifications would be you're going to go grab a jacket, right? Or go inside. But don't use that for this one. Good. Are there any questions on this one?
Oh, yes, I have a quick question, Professor.
Go ahead, Shane.
So basically, if it's about releasing heat or bringing your body temperature down, your blood vessels are going to constrict.
So if it is about bringing body temperature down, the blood vessels and the surface of the skin are going to dilate. So you have two sets of blood vessels. You have blood vessels on the surface and blood vessels that are more deep, superficial in the skin, right?
Mm-hmm. Correct.
And so if you're hot, you're going to shunt blood to the surface to release heat. If you're cold, you're going to shunt blood away from the surface to keep heat in the core more.
Okay.
Okay, so for this one, vasodilation of blood vessels goes with trying to release heat. Okay,
Okay.
it goes with this one. And then if we're trying to keep heat, these blood vessels would vasoconstrict. So you could do the same thing here. You could say sweat glands and blood vessels would be the effector, and then you're just going to decrease sweat or stop sweating, and then you're going to vasoconstrict those blood vessels. That would be acceptable too.
Okay, so I got that right. I got that right then, because I had worked on the lab a few days ago, and my physiological error was my body temperature was actually down. But I know that in the lecture we talked about it being higher than usual rather than it being down. So I kind of did, I didn't guess, but I looked at, the differences between the blood vessels, and I would assume that it constricted, but I wasn't too sure in understanding it, but now it's a lot more clearer.
Good. And on average, they're finding that people's body temperature has been dropping like over the decades or whatever. So it used to be 98.6 and now it's a little bit lower, which I think is interesting because with global warming and our environment increasing, people who work outside in agriculture near the equator of the earth are actually overheating, and they're having sudden kidney failure, and they're dying because of this kidney failure because they're overheating, because the temperatures are so high and your kidneys can't handle it. They can't process it. So I'm not quite sure if they're linked or not, but it's really interesting to think about like how animals are changing and how we're changing because of global warming, or how we're evolving, So, okay, but yeah, that's good. Pedro, did you have a question or comment?
Yeah, I just had a quick question. So this is just an example what we should do in our own lab, correct? For the stimulus, sensor, integrator, effector, and the rest, right?
Do whichever one you want to do. Yeah.
Okay, that was all.
But I want you to know both for the lab exam.
Yes.
So you'll see some type of question like this, like, hey, you guys went out to Joshua Tree. It's 100 degrees. How are you going to regulate your body?
Okay.
You'll have to fill it in. Good. Okay, let's go to respiratory rate. So this one is a tough one. I will tell you that I don't ask this on the first exam. I usually ask it on the second exam, the lab exam, because it's hard it's hard for this one to stick with students. Okay, so your mechanism to breathe is an increase in CO2, right? In the plasma. Did anybody find a sensor for this?
Chemoreceptor reflex.
So remember, you're giving me a sensor and you're giving me a location. So chemoreceptor and location.
Aortic arch.
Good. So in aortic arch.
How about blood pH? Because the CO2, it was talking about it affects the pH of the blood.
Yeah, that's fine. It's the same, it's going to be the same receptor. So let me rephrase that. That's a good one, Rena. Let me rephrase that. So a lot of CO2 is going to cause a lot of H plus or protons or acid, and that's going to drop the pH. I don't expect you to know that now, but we're going to talk about it once we get into respiratory system. And that's why I don't like asking this one for the first lab exam, because you guys don't have a full grasp of it. But yeah, it would be, it'd be a drop in pH too. These guys are going to get excited if there's an increase in CO2 or a drop in pH. So they're in the aortic arch. And did you find another location in the body?
Carotid cavity.
Good. Carotid sinus, right? So those are the two. So you have chemoreceptors. Let me show you. You have chemoreceptors coming off the heart. So the aortic arch. So you have them right coming off the aortic arch going to the body. And then you have them in the carotid sinus. So if you feel your larynx, you guys, your voice box is like right here. Your carotid sinuses are in really deep, like on the backside, almost by your vertebrae. So aortic arch and carotid sinuses. So going out to the body and going up to the brain. This is where you have those receptors. And these receptors sense CO2 and protons. And so as CO2 goes up, these guys get more excited and they keep chattering to the brain. Okay. You also have them in the brain. I don't want to focus on that right now, but you also have them in the brain. And it's in the spot that is the integrator as well. So what is the integrator for respiratory rate?
Medulla,
Oblongata.
Good, you guys.
the medulla oblongata. And pons, I have pons.
Pons oversees it.
Okay.
But
So
that's
just
fine.
medulla oblongata.
Yeah, just medulla oblongata. Mhm. Good.
And so for the sensor, instead of putting the blood pH, it's just best just to put the aortic arch or the carotid sinus.
Yeah, because you're identifying the sensor and the location. So the chemoreceptors are the sensor and they're found in the aortic arch and carotid sinus. And it's going to be the same whether you're talking about CO2 or whether you're talking about blood pH. Because both of those trip up these chemoreceptors. They're kind of like smoke alarms, right? If CO2 goes up or if blood pH changes, they're going to get triggered.
So then does that mean then blood pH is actually a stimulus then?
It is, but I don't want you to focus on that right now.
Okay.
It is. I want you guys to understand one of the pieces first, and then we're going to add more detail when we get to respiratory system. But you are correct. Yeah, I want you guys to make it easier when you're first learning these. Okay, so increase in CO2, chemoreceptors in the aortic arch and carotid sinus get triggered. They send a signal to the medulla oblongata. Medulla oblongata says, hey, that's too high. We need to cause it to go down. So where are they going to send that signal to?
My best guess was the blood vessels or the alveolar sacs in the lungs.
Okay, that's a good guess, but think about it. Do the lungs contract and expand based on themselves, or do they have muscles driving that?
Diaphragm.
Go ahead, Anthony.
Diaphragm.
Go ahead.
I was gonna say breathing muscles like the diaphragm.
Yeah, perfect.
Diaphragm, yeah.
Good. So let's see. So the muscles, the skeletal muscles. So diaphragm.
Rib muscles.
Yep. And give me one more, external intercostals.
Intercostal muscle.
Yeah, it's the external ones. It's the ones on the outside of the ribs. Like when you think of eating ribs or rib meat, it's the ones that are outside that they go in this direction, if that makes any sense. No, wait, they go in this direction. Yeah, because you're pulling the ribs up and out. So the diaphragm is going down and you're pulling the ribs up and out with the external intercostals, right? And so the diaphragm and external intercostals are going to do what, Tammy?
Decrease the CO2 level.
But before that, that's the result. What do they do?
Increase rate and depth of ventilation.
Perfect. Increase rate and depth of breathing.
Professor, I have a question. For the effector, if I put intercostal muscle, so it's wrong, right? I have to mention external,
Correct.
right?
'Cause-
Okay.
Yes, you're correct, because internal intercostals, only internal intercostals are used when you're taking a deep breath in. So internal intercostals are used when you are, no, forcing it out, sorry. When you're going like that, you're using the internal intercostals and they're actually contracting and pulling the ribs down. So they are responsible for deep inhalation. They're responsible for the opposite. I'm saying that completely wrong, but that's okay. No, don't put in internal intercostals.
So don't put lungs, just the diaphragm or the external intercostals.
Yeah, the lungs are not the driving force. You have to have that diaphragm contract and those external intercostals contract in order to get air to move into the lungs.
Okay.
Yeah, but that's a good guess. And everybody guesses that, which makes sense. Good job, you guys. Okay, let's go over the last one then. So pulse rate. Let's do a drop in pulse rate. Okay. So a decrease in heart rate is the same as a decrease in pulse rate, right? And you guys will learn that blood pressure is linked to heart rate. So in actuality, it's a decrease in blood pressure that will follow. They're linked together, but we're going to keep them. We're just going to focus on heart rate right now. So what's the sensor for that? Give me a receptor and give me a location.
The location is the rib. We can take it the pulse in the rib.
Give me the receptor first. So is it a chemoreceptor?
Baroreceptor.
Good. So it's a baroreceptor.
Well.
In aortic arch and carotid cavity, just same
Good.
as the
So we answer all of them or just the baroreceptor?
You're going to give me all of them. So Mary, one of the things is, and I couldn't quite understand you, but you need to be careful. We're not concerned with where we take pulse. We're concerned with where these baroreceptors are located. And so baroreceptors are located in the same spot that the chemoreceptors are located. So baroreceptors in aortic arch and carotid sinus. Right? In aortic arch and carotid sinus. And these baroreceptors are wrapped around those arteries. And so when blood goes through them, they stretch. And the rate of stretch and the magnitude of stretch can be interpreted by the brain. Okay. And so what these guys are going to stretch and send impulses to the integrator. What is the integrator?
medulla oblongata.
Perfect. It's the same one. So medulla oblongata is going to say, hey, heart rate's too low. We need to send a signal out to get it to go up. There's two effectors. Evelyn, do you have one of them?
I don't know. I think I'm wrong.
No, go ahead. What do you think? It always helps with discussion. So what do you have?
I'm a bit lost. I was saying that for the if I have a question for the integrator, can it be carotid sinus as well? Or
no, because that's where the sensors are. And so the sensors are in the carotid sinus and in the aortic arch. and they stretch and they send action potentials to the medulla oblongata. So they're connected via a nerve. You can't really see that, but they're connected via a nerve. So there's nerves that send the signal to the medulla oblongata, which is the region of the brain that interprets the signal coming in. Good. And so the medulla oblongata is then going to send a signal out. What did you have for this, Evelyn?
I don't know.
Okay, that's okay. Rena, what did you have?
Blood vessels and the heart.
Good. Okay, so we're
Oh.
looking. Go ahead, Evelyn.
Thank you. I'm sorry. I'm like scared to be wrong.
Oh, that's a valid one, right? You're scared to be wrong, but I will tell you that I mess up all the time. And we're all learning this together. So try to get over your fear. I'm not gonna like yell at you and nobody really cares. So you have to, it's a work in progress, but I get that.
You're not alone.
Yeah, we're all trying to learn this together. Go ahead, Shane.
Yes. What's the difference between the carotid sinus and the coronary sinus on the heart?
Oh, carotid sinus is the carotid arteries going from your heart up to your brain. Okay.
Okay. Yeah.
Coronary artery is around your heart. So coronary
Right.
artery supplies blood to the heart. Carotids supply blood to the brain. So when you think of monitoring stations for your body, you really want one monitoring station to be in the aorta so that it measures what's going out to the body, and then one measuring station in the carotids so it's going up to, so you know it's going up to the brain.
Okay, cool. I just need a refresher.
Yeah, good. Okay, Anthony, what happens next then? So what's the response? What is the heart going to do?
Okay, so we have a decrease in the heart rate, right? So I want to say the blood vessels and the heart are going to constrict, so that way they give a pump.
Good.
Yeah.
And what does the heart do?
The heart speeds up.
Awesome. So your heart is going to increase heart rate. You'll get a better picture of this when we get into cardiovascular system. I don't want you to go through the whole thing. So if you went to tutoring and you had Richard, he probably gave you the whole kitchen sink. You don't need to know the whole kitchen sink. So I can always, never mind. I can always tell when students go to Richard because they have like these crazy complicated answers for some of the stuff. And I'm like, where did you get this from? Did you go to Richard for this? Yeah. I'm like, oh. Okay, so increase in heart rate, right? And then your blood vessels are going to constrict. So if heart rate goes up and the blood vessels constrict, that's going to cause heart rate and blood pressure to go up, okay? So by the end, you're going to have an increase in heart rate. But remember, I told you that they're linked, so increase in blood pressure.
And excuse me, and you have to mention the increase the blood pressure and back to the set point, right?
Yes. So your heart rate has dropped, and then by the time you go through the whole thing, heart rate should increase. And we're not really worrying about blood pressure right now, but it will follow suit. And it's, if heart rate is low, then blood pressure is going to be low, and this is going to correct it. What happens if, did that answer your question, Najma?
Yes, thank you so much.
Okay, it's hard, you keep breaking up, so I would just want to make sure. Okay, so let's see. So if we had an increase in heart rate, would this be the same? Would the sensor be the same?
I would say yes.
Yes.
Okay. Would the integrator be the same?
Yes.
Yes.
Good. Would the effector be the same?
Yes.
Mm-hmm.
And then what is going to happen with the response, guys? Mary?
I don't know. I'm so confused in this part.
That's
So
okay. Look at what we have here. So if heart rate's low, you're gonna increase heart rate.
Yeah.
So then what would we do to,
Increase?
no, because right now it's high. So how are we gonna get it to go back down?
Oh,
That's okay. Decrease heart rate, and what are the blood vessels gonna do? Instead of constrict, they're gonna do what? Vasodilate. Let me write it down here. Okay, and I know that these are hard, and I know these are weird, and I know it's hard to conceptualize them. What I would like you to do is just keep writing them over and over again. So when I say work through the feedback loops, go ahead and write them and diagram them out, diagram them out, diagram them out. I do this with a dry erase board. You can do this with, you can print out a piece of paper and put a cover over it, like a plastic cover, and keep drawing with the dry erase marker pen, or you can just draw them out on your computer, right? Whatever makes them stick. Good. But you will see this one on the lab exam, and you will see body temperature on the lab exam for sure. Yeah.
And so, so when we go to that body temperature, and then let's say somebody is experiencing they're cold, it's the same thing as just the receptor. What will change? The effectors will change.
No, it wouldn't. Nothing would change in the system. That's a really good question, Anthony. So nothing would change. So let's say the temperature is low, right? And they start to shiver, but body temperature doesn't go back up. So they don't get body temperature back up, right? Because what does it mean for a disturbance? A disturbance means you can't get back to your set point. So body temperature dropped, and regardless of how much you're shivering, how much heat you're generating, body temperature is still low. So that's a disturbance. And so instead of filling out the feedback loop like that, you just would mark, it's a disturbance. Like, let's see, hypothermia is a disturbance because why? How would you say that?
I have a question. If you have hypothermia, if your temperature is dropping, I thought that because you have here skeletal muscles, so you start to shiver to produce heat. Your muscles are also contracting, correct? So why would the temperature not? Oh wait.
Let's say
go up.
Let's say you fell into a frozen lake. So you're generating heat, but you're losing it faster than you can generate it. So that would be an example. Another example would be, let's say I'm out on a mountain and a storm comes in, and I get wet and cold, and I'm losing heat faster than I can generate it. So there are situations, usually not generally walking around, but you can get hypothermia in 55-degree weather. And I don't think that a lot of people realize that. Right? But if you're not generating enough heat, and usually it's if you're wet, you're losing way more heat faster. And if it's cold and you have that wind blowing on you, you're losing heat way faster than you can generate it sometimes. And so you got to be careful. So hypothermia would be a disturbance because you can't bring body temperature back up, right?
So then your result would be just disturbance?
Yeah. So this is a normal pathway. If body temperature is low, you bring it back up. And that is still the pathway for hypothermia. It's just, it's not resulting in an increase in temperature.
Could you say that a disturbance is somewhat similar to a positive feedback loop then?
No. You could say that, but that is incorrect because a positive feedback loop, you're amplifying. So the result is amplifying the stimulus. And so, and that is normal. Okay. With losing body heat, that's not normal. That's a disturbance. So I get what you're saying. And you can kind of say that, but that's a slippery slope. Because technically a positive feedback loop means that it naturally increases it. So if body temperature drops, my body is going to drop it lower, and that doesn't normally happen.
Got it.
Yeah. Good. Any other questions, comments?
And then I'm just curious for that, for the set point, what about people that are always cold? I'm imagining if somebody is always in the 96, I don't think that a set point, the body is trying to bring it back up.
No, and so if my body temperature, and my body temperature is not 98.6, my body temperature is around 98.3, right? But I'm not always cold because I am obese, so I'm always hot. But there's variations on the theme, right? So everybody's set point is going to be slightly different. But we're not taking into account hyperthyroidism or hypothyroidism or circulation issues. Those are all disturbances, right? So we're not even thinking about the pathophysiology. We're just trying to understand how it normally works. But if somebody's always cold, it could be a thyroid problem. It could be a lot of things. So it could just be that they need to wear more clothes or eat something, you know, I don't know. But we're not worrying about that. Go ahead, Irina.
Okay, so just as you said, so on my set point, when I was going through, you know, just trying to figure out, I have two. It
Mhm.
said to use both. I'm at 56 or 60 beats per minute. And so I put in for
Average
two.
them. Average them.
That is like when I finally set them all out, I did the average and they're both, it's at that 56 to 60. So
Wait, hold on a second. So how many, did you have one number that occurred the most?
they both were the same.
Oh, I see what you're
So,
saying. Okay, so
yeah,
then,
so when I went on Khan Academy, it said if you have two numbers that are like, you know, when you put them all out to 10 and they both have the equal amount, then to use both.
okay, so I want you to average them. So 56 and 50, you're just gonna add them up and divide by 2.
Okay.
Eventually, theoretically, if you kept taking your measurements, if you took like 3 more, you would hit one of those numbers. But you don't have to do that.
Okay. And I am always cold.
Well, to be fair, it has been cold lately, so no. Great job, you guys. Great job, you guys. And it's okay if you don't understand it. If you're completely lost, say you're completely lost, and then I can help you.
Professor, I have a question.
Go ahead, Rita.
So since Rena is going to average her 2 scores when we do our graph, do you want us to do it all over again? Because I had already done the graph based on those 2
Oh,
values.
no, that's fine. Whatever graph you have, that's fine. Don't worry about it.
Okay.
Mhm. I know there in some groups, there was only 4 people who put in their number by the deadline. And so students are like, what do we do? I'm like, just graph those 4 numbers. That's what you have. That's what you have to work with. You know, that's reality.
Yeah, I was also gonna say, Professor, no one really chose the second column. It was really just third and the first. So yeah.
Okay,
So it was
so
either we didn't work out at all or we worked out 3 or more times a week.
Yeah.
that's evidence for lockdown, right? Okay, so
Right.
we're
So
on.
are we still safe to turn this in on Friday and get full credit? Because that's what I had emailed you, like there was only like one other person beside myself that put stuff on.
Yeah, that's fine.
And then it started trickling in.
That's fine. Yeah, whatever you.
I didn't know. I saw it late, so I did it. I put mine the next day.
That's fine. No problem. Don't stress. I don't care. I just want you guys to participate. So it's fine. And so I think, yeah, so it's like, we're virtual. So are you super stressed out and you need to exercise a lot? Or are you so stressed out that you have to sit there and you can't get up and work out?
I guess it's either or.
I know, right? That's awesome. Yeah, no, that's fine. Whatever data you guys have, you have. Don't worry about changing it. And if you added it late, that's fine. That's okay. We're just trying to get through this. Go ahead.
Professor, I just had a quick question about today labs. Honestly, it was kind of complicated for me. And do we go just like the homeostasis lab worksheet through together, that would be really great. So it's really feel,
Yeah.
it makes me feel comfortable to understand better.
Yeah.
Is it possible for you?
Yeah.
I try to study before the class. I try to
Right.
go to the tutoring, but that would be great if we do together.
Yeah. So what I want to do with you, Nejma, is what we can do is, can you come to my office hours on Monday from 11 to 2? Okay.
Sure, of course.
And then we can go through it, work through it on a piece of paper and try to figure out how we got the measurements. And then we can go through it on Monday, and then remind me, guys, we can go through it in lab on Tuesday. So we'll review it on lab on Tuesday. So just that we're on the same page.
Thank you so much.
Yeah, of course, no problem. I know this lab is crazy. Usually you guys, you're rushing and you don't even know what the heck you did because time's up and you have to clean up and you're running out of lab. So that doesn't surprise me at all. But watch the video, work through the material, read the handout, draw your pictures, try to figure out what's going on in the experiment, outline it, and then we'll meet on Monday and it'll make more sense. Then I have time to sit down with you and go through it individually. Yeah, and if a couple of you guys want to show up at 11 and go through it, that's fine. Or however many, if the whole class wants to show up, I don't care. That's fine. All right. Okay, guys. Take care of yourselves. I'll post this when it's done.
All right. Thank you, Professor.
Bye. Have a
Thank
great
you,
day.
Professor.
Be well.
Bye.
All right, thank you.
Bye.
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 Professor.
Can I talk to you before you leave in?
Yeah. Hang tight.
Oh,
Yeah. Just
it's
one
Mary. So let's see.
Evelyn,
Yes, I have one question too as well.
go ahead.
Oh, for my paper, I have a subject already, but a topic, but I'm not sure if I can do it on eczema,
Yeah,
like
that would be awesome.
how that affects the body, because
Yeah.
it applies to my life. I have eczema, but I want to know more about it because it's still new.
Yes. And there's a lot of research out there too. So it'll be interesting to see what you find. Yeah, that's awesome.
Okay, then thank you. That's all.
You're welcome. Bye, Evelyn.
Thank you. Bye. Have a good one.
Mary?
Yes, teacher. So it's something personal.
Oh, okay. Hold on. Whoops, crap. I just saved it. Pedro, do you have a quick question? Go ahead.
Yeah, I just have a quick question. What textbook was free? Is it just the OpenStax one? And you can get like a physical copy, or
No, you can get a physical copy of one of the Pearson texts. It's a human physiology text. So
is it on the syllabus?
I don't think it's the one that's on the syllabus because that one was back ordered. It might be that one. It might be a loose leaf copy of that one. I'm not sure, but it's one of the straight physiology ones. It's like the 200 or 300 level, like the upper level human physiology. So it'll be good for your programs. So if you have time, go by the bookstore and pick one up. Yeah.
Oh yeah, you just show your ID and it's like, oh, I'm in bio 261, and they'll be like, oh, okay, then we'll order it for you if it's not there, or if it's already there, they'll give it to you.
Yes.
Oh, okay.
Exactly.
Thank you so much.
You're welcome.